Okay, let's dive right into this explainer and see how we can teach machines to draw boundaries between some seriously tricky sets of data. We hear about machine learning all the time, right? But the actual mechanics of how a computer makes a decision can often feel like this impenetrable black box. Well, today, we're going to crack that box wide open and break down one of the absolute most powerful tools in data science.
It really begs the question, how do machines know exactly where to draw the line between two incredibly complex, totally overlapping categories? Honestly, it's the fundamental problem of classification. And to really grasp the elegant mathematical solution known as support vector machines, we first need to look at why our basic, everyday classification sometimes completely fails us when the data gets messy.
So Section 1, the basics of classification, drawing the line. Picture this. We've got a really simple one-dimensional number line tracking the mass of a bunch of mice. Our non-obese mice are all clustered together on the left side, and our obese mice are clustered over on the right. Now, when we get a new mouse to measure, we need to classify it based solely on its mass. The absolute simplest solution here? Just pick a single threshold point right on that line. If we place that point exactly halfway between the inner edges of the two clusters, well, any new mouse that falls to the left is classified as not obese, and any mouse to the right is classified as obese. Easy enough, right?
Now, a quick terminology alert for you here. The shortest distance between those edge observations and our halfway threshold is called the margin. And because we place that threshold perfectly in the middle, it gives us our largest possible margin. This means we're using what's called a maximal margin classifier to make our predictions as safe and cushioned as mathematically possible.
Sounds perfect in theory, doesn't it? But wait, what if our training data throws us a curveball and has a wild outlier? Let's say one single non-obese mouse is unusually heavy, like far heavier than its peers. Because our maximal margin classifier strictly relies on measuring from those extreme edge points, our threshold point gets shoved way over to the right just to accommodate it. Suddenly, our whole model is super sensitive to just one weird data point. And frankly, a model that's sensitive is pretty lame.
Which brings us to Section 2, handling tricky outliers in the bias-variance trade-off. So, can we do better than a rigid threshold that gets entirely derailed by one heavy mouse? Absolutely. We do it by learning to purposefully accept a few mistakes. This brilliantly illustrates the famous bias-variance trade-off that plagues literally all of machine learning. See, the maximal margin is highly sensitive to training outliers. It has low bias, but high variance when presented with new data. But if we use a soft margin, we intentionally allow for some misclassifications. We essentially just ignore that heavy outlier. Now, this gives our model a higher bias initially, sure, but extremely low variance, meaning it performs much, much better when we test it on brand new data.
And here's where the magic terminology comes in. When we intentionally use this soft margin to allow for those misclassifications, we're using what's called a support vector classifier. We use a neat statistical method called cross-validation to figure out exactly how many misclassifications we should allow inside that margin to get the absolute best long-term accuracy. Oh, and the name? It comes directly from the observations that sit right on the edge and within that soft margin. Those specific data points are quite literally called the support vectors.
All right, moving on to Section 3, the overlapping data problem, when lines fail. Okay, support vector classifiers are great for dealing with outliers, but what happens when our data completely overlaps? Imagine a drug dosage dilemma. We're testing a new medication. The patients aren't cured if the dose is too low, but they also aren't cured if the dose is too high. The drug only works at a just right medium dosage. If we map the success and failure data dots on our one-dimensional line, the red dots for failure and the green dots for success overlap perfectly in the middle. There's literally no single spot to cut that line to separate the colors. So what do we do? How on earth do we draw a line when the data completely overlaps? Since maximal margins and even our flexible support vector classifiers totally fail to separate this kind of data, it is high time we upgrade to the actual star of this explainer, the support vector machine.
That brings us to Section 4, moving to higher dimensions, lifting the data.
To escape this messy one-dimensional overlap, we can use math to literally lift our data out of the problem. Start with our original x-axis, the dosage. To fix our issue, we just square the dosage to create a brand new y-axis coordinate. For example, if the dosage is 0.5, the y-axis becomes 0.25. By applying this simple math to every single observation, we magically transform our flat 1D overlap and pop those dots up into a 2D curve. Suddenly, in this two-dimensional space, we can easily draw a straight line right through it to separate the cured patients from the ones who weren't. So, the crucial takeaway here is that a support vector machine is incredibly systematic. It always follows these 3 simple steps to untangle overlapping data. Step 1. Start with data in a relatively low dimension. Step 2. Move the data into a higher dimension. And step 3. Find a support vector classifier that cleanly separates the groups in that new space. That's the core logic. Let's rapidly track how this builds dimension by dimension. When we only have 1D data, like our initial mouse mass example, our classifier is just a single point on a number line. In fancy math jargon, that point is called a flat, affine, zero-dimensional subspace. Now bump it up to 2 dimensions, like if we were measuring both the mass and the height of those mice. Our classifier stretches out from a single point and becomes a 1-dimensional line. Add a third measurement, say age, and our data is now 3-dimensional. That separating line then flattens out into a 2-dimensional plane, acting as the boundary in that 3D space. But what happens when we hit 4 dimensions, like measuring mass, height, age, and blood pressure all together? We can't even visually draw that. So mathematicians call a classifier in 4 or more dimensions a hyperplane. Technically speaking, all of these flat, affine subspaces we just talked about are hyperplanes, but we generally only use the term when our human brains can no longer visually draw it on a piece of paper. And that leads us to our final section, Section 5, Kernels and the Math Trick, Math Magic. Now you might be thinking, back when we were looking at drug dosages, how does the machine actually know to square the dosage instead of cubing it? Well, to make all of this complex mathematics possible, support vector machines use tools called kernel functions. The polynomial kernel systematically increases dimensions step by step using a degree parameter called d, basically trying squared, then cubed, checking relationships until it finds a clean boundary. But then there's the radial kernel, also known as the radial basis function. This one mind-bendingly maps relationships in infinite dimensions. Since they obviously can't fully comprehend infinity, practically speaking, it behaves kind of like a weighted nearest neighbor model, relying heavily on the closest data points to classify any new observations. And this brilliantly illustrates what data scientists affectionately call the kernel trick. You see, calculating actual infinite dimensions would instantly crash any computer. But the kernel trick mathematically calculates the complex high-dimensional relationships between data points without actually having to perform the grueling math to physically transform the data. It calculates the relationships as if the data were already in those higher dimensions, which saves massive, massive amounts of computing power. So I want to leave you with this final thought. If a machine can map infinite dimensions to instantly solve complex overlap, what boundaries in our real world are waiting to be drawn? By gracefully leveling up from a simple point on a line to a high-dimensional hyperplane, support vector machines show us that simply changing our perspective can make the impossible completely possible. I really hope you've enjoyed breaking this down with me today. And hey, keep looking for the hidden structure in the data all around you.